Now you can hear me, right? You can hear me? And now I'm surrounded here with noise.
Good morning, everybody. Are you well rested? Who has had some fire alarms going last night? Okay, hi neighbors. Okay, so first a few announcements before lunch. Please remember that we have a group photo, or learn it now that we have a group photo on the terrace outside. And for all the photos that you have taken during the workshop and you want to share it with the world, please do so at the Matrix channel or just send them directly to Ralph or Maria. Understood? Okay, now without delay, I'm going to completely mispronounce the surname of the physicist extraordinaire Johann Meschenop. Did I do it correctly?
Perfect.
Okay, cool.
Perfect.
Please give him a warm welcome to the stage.
Yeah, thank you. And also thanks for the organizers for inviting me. So I don't know too much about radio, GNU Radio, so that was the first time I heard about it, to be very honest. So I hope at least I can give you somehow a perspective on, I'm a researcher at FAIR, and I'm a researcher at GSI. I came actually from the Netherlands 3 years ago. I was there for 25 years or so, an associate professor. And I moved here because of essentially this particular facility, because I like it so much. This is the future also, hopefully for me, before the retirement, I hopefully also will be able to see this beautiful facility being ready and enabled to run physics with these FAIR accelerators, right? And the reason why I was so enthusiastic to move to GSI and FAIR, well, first of all, I was already connected to GSI and FAIR, but somehow I had to stop my research in the Netherlands, is because I like the facility because it has a lot of research topics which it addresses, from atomic physics, material science, biophysics, particle physics, nuclear physics, hadron physics, this is what I'm doing by the way, heavy ion physics. So there's a very broad community with a lot of physicists on an international level, connecting also to other research facilities like for instance CERN or a J-Park or a J-Lab in the US and Japan, which makes it very exciting to do research here, right? And the nice feature of FAIR is this high intensity, being able to do precision, do forefront kind of physics. And I will hopefully also give you somehow a flavor of that. But I will also connect it to technology, in particular to software development. And hopefully I also somehow resonate with you guys and see how that works out, right? Okay, but I have to make a confession. I already said it, my background, I'm a physicist. I'm not a software engineer, although I'm actually the FAIR computing coordinator for the FAIR experiments. So in that sense, it's more or less a self-educated, if you want, software engineer, right? If any. I mean, I'm already now, 53 years old, so I think already the younger generation knows much more about things than I do. But nevertheless, my background is physics, I'm not an engineer. So that's one thing. The other confession that I make, GNU Radio, I only learned about it very recently when Ralph actually invited me to give here a talk, right? So I was also thinking, so GNU Radio is something interesting. So I asked my colleagues in the same experiment where I work at, and they say, yeah, no, we don't know what GNU Radio is. So I asked, of course, the holy grail of anything is, of course, JetGPT to help me out here, right? So I asked her, how can I use GNU Radio 4.0, that seems to be the new version, doing hadron physics, but that's what I do, I will explain later on what it is. How can we connect, right? That's basically what I asked. So, and of course, ChatGPT is always very positive, so it starts with very positive statements about what it knows about GNU radio, what it knows about hadron physics, what are the topics over there. Now, yeah, this particular text I could also think of how to write there. But then it really became extremely creative. This is extremely creative. Let me show you here. So it came with suggestions. Point 1. Yeah, maybe do something with signal processing from detectors. Yeah, of course, that's an item which I'm also dealing with, right? All kinds of suggestions. Another one here, real-time data acquisition and monitoring. Yeah, this is certainly something common between us in a certain way. Timing, synchronization, absolutely. Data analysis, even higher level now, data analysis, event reconstruction. Yeah, that is also the big business what you're doing in a hadron physicist experiment. Simulation, prototyping. Yeah, we have to prepare the experiment, we have to do simulation, so maybe we can connect there. Or doing network data collection or training. So it came with all kinds of suggestions. If you read them, yeah, they somehow make sense. I mean, then I also start wondering, wow, maybe somebody wake me up. Maybe I'm missing here something. Maybe there is something which we can somehow share with each other, right? That's the first thing I learned from this particular exercise. The other thing is, who says that AI cannot be creative? I will come to this particular point also later on again, because I do think that AI is really becoming something interesting. But okay, later I will talk about that later. Okay, this talk, the objectives, couple of them. I will talk about science and technology at GSI Fair, the why, the how, the what. I will not discuss the whole fair experiments and research activities, but I focus very much on what I personally do. Right, so that is, I think I also feel a little bit more comfortable talking about this. I will talk also a little bit historically, you know, from the past, the present, and the future. It becomes a little bit like a roller coaster in a certain sense, but I think there is a certain thread in my particular talk, right? So be aware, this is what I'm trying to somehow convey to you. And hopefully we come back to this JetGPT kind of question and see how we can actually, you know, communicate with each other. Okay, few words on the why. I'm a hadron physicist. A hadron physicist is a physicist who's looking essentially at elementary, on the elementary level, on the femtoscale level, to particles. So here we have an atom. Let me try to find the pointer here. So here we have an atom, right, and then we have the atomic nucleus, nuclear physics, and I'm interested to look at the building blocks of an atomic nucleus. These are the protons and the neutrons. So that's, for instance, an example of a typical hadron. But there are many hadrons. Now, hadron has a meaning. Hadron means massive, bulky, lumpy, or whatever. That's essentially the Greek name of hadrons, in contrary to leptons, which is small and tiny. So you might wonder, so what is now so massive about a hadron? So let's just look at a proton, some numbers of a proton or a neutron if you want. Let's look at some scales here, right? Okay, a proton has a mass about 10 to the minus 27 kilograms. Well, that's not very massive. We like to always put it in different units. E is mc squared, so the mass is the energy divided by the light velocity squared. So we say 940 mega electron volt over c squared, so about 1 giga electron volt. That's the typical mass. This is small, right? So that's not very massive. The size of a proton is in the order of 1 femtometer. So this is why we call femtoscale research. It's my title of my talk, right? So that's in the order of 10 to the minus 15 meters, right? Also not very massive, I would think so. But if you now look at the mass density, how much mass per unit volume a proton contains, this is actually impressive. It's 10 to the, you can calculate it yourself, not so complicated, right? Assume that it's a sphere, right? 10 to the 18 kilograms per cubic meter. That's the mass density of a typical hadron, the proton or the neutron. It's a huge number, right? Just to compare the density of the Earth, 10 to the 3, 10 to the 4. Yeah, and if you really want to go on an astronomy level, yeah, a neutron star, for instance, they're getting close to it, 10 to the 17, right? But you really have to go to extreme objects in the universe to find something equivalent to a mass density of a hadron, right? So by studying hadrons, you study mass. That's the whole thing of what we're trying to do in hadron. This is the why, right? Okay, you might think, but we know what a proton is. You know, wasn't that these quarks, right? There were, you know, these up and down quarks, elementary particle standard model. You put 3 together and you have a proton, right? Well, I will disappoint you here again, because look at the proton mass now again, right? The quark mass, we know that's the Higgs mechanism. That's what they figured out. That's certain, for instance, right? A quark has a mass of the order of a couple of mega electron volt. 3 of them give you in the order of 10 mega electron volt. a proton is like 1,000 mega electron volt. So only 1% of the proton mass comes from the Higgs mechanism. Right? So understanding the mass is apparently this is not that simple, that picture. This is more like this. There's all kinds of dynamics going on. Some funny dynamics going on which create mass. This is of course something that has to do with the interactions of these quarks. It has to do with the force carriers of the quarks. For whatever reason, it generates energy. And this is something which we try to understand. The origin of mass. We really do it here. Right? So that's the reality. Okay, so and that all has to do with a theme which is called the strong interaction. The strong interaction, the interaction between what we call color charges. That is essentially where the key is, what we're trying to understand. Now there is an equation around it. I mean, you see on my t-shirt there's also this funny kind of equation. This is the wrong one. This is the Higgs mechanism. We don't like that. We like that equation. That's quantum chromodynamics. That's describing, if you want, the equations of motion in some particular way of color degrees of freedom, quarks, right? Now, like radio waves, you have electric charge. You wiggle electric charge, you get radio waves. If you wiggle a color charge, you get gluons, gluon waves, right? This is what we are studying, gluon waves, right? And this has a certain particular interesting dynamics which we don't yet understand. We know the formula of this. You cannot calculate it, from first principle. It's very complicated. And even if you would be able to do it, and there's a lot of people trying to do it, it still is a question of what is really behind it? What is really the mechanism which creates then the masses of these particular hadrons? What is the original mass? What are the properties of hadrons? How are they actually being formed? What are the underlying symmetries? This is the questions which we're trying to understand, and this is also where FAIR is contributing. These are the three, if you want, big collaborations. One is now left out, that's the atomic physics here, which are trying to address this quantum chromodynamics. And that's already a theory which is 50 years old. More or less when I was born, this theory came about. That's the standard model. The interactions of quarks, these are the quarks here. This is the standard model, up, down, and that is what the protons and neutrons are made out of, right? But you also have heavier quark charm and strength, which we can do with FAIR. And we can try to see how hadrons are being formed out of the quark by these gluon kind of mechanism, right? Okay, so that's the thing. Now, how do you do this? How do you start? Well, first of all, you have to come with a collaboration, right? And the collaboration, what we're talking about, is in the order of about 500, 400 people or so. This is actually the picture of the Panda collaboration, already from quite some time ago. And the way to do it, let me just conceptually give you an idea how you study these particular hadron mechanisms at FAIR. Well, you start with ordinary matter, and I put the analog like a house. You want to understand what is making a house as it is. What makes a house stable, for instance, right? What are the properties of a house, right? So what do you do in order to understand the details of a house? Ordinary matter, a proton, for instance, ordinary matter in our case, right? Well, what you can do, for instance, is try to stretch it. Try to see when it starts breaking down, put different bricks in there, different colors, and see when it reaches its end of stability. This is what you do here. For instance, if you go to Darmstadt, you have these kind of funny buildings there, right? I mean, or you go to the Netherlands, you have also these exotic buildings at the University of Groningen. Where is the limit of stability? And you hope by going to extremes, to extreme matter, to learn something about the ordinary matter, right? You try to stretch it to a limit, and by hoping to see where it starts breaking it down, or what the properties are of these kind of things, you hope to learn something about the underlying matter. That is essentially, conceptually, what we do at FAIR. Now, in hadron physics, you might also know, of course, we have ordinary matter. So these are the house, if you want, the protons, the baryons, and the mesons. These are called the protons, for instance, the neutrons. There are also particles which are made out of quark and antiquark. That's called the mesons, pion, for instance. These are ordinary matter. But if you ask somebody who knows about quantum chromodynamics, they also, but in principle you can also form exotic matter. You can also have matter made out of 4 quarks or 5 quarks. You can also have matter which is made out of these gluons, these waves, these strong interaction waves, if you want, creating a certain massive particle without any quarks. All these things in principle is there, but we have to look for it. This is what, for instance, this Panda experiment is trying to do. Also, my friends from the heavy ion physics, you already saw yesterday these pictures of these heavy ion, particles accelerated and they bang on other heavy ion and you create all kinds of very dense matter with all kinds of different particles. Well, their aim is try to understand the so-called phase diagram of quantum chromodynamics. Like you have for water, you have different phases, a solid phase, a liquid phase, a gas phase. Also in this QCD matter, we expect to see these kind of phases. And of course, one of the things which we like to do at FAIR is to look at very dense matter. So be somehow related to, for instance, the properties of a neutron star. Another form of creating exotic matter. And if you talk to my friends of nuclear physics, well, they also look at extremes of nuclear matter, right? This is a nuclear chart, you also seen it yesterday, and the extreme thing is trying to look at nuclei where you have many, many neutrons in there, and see when they are starting to be unstable, and looking at these particular properties. This is, again, the same kind of philosophy. And the other thing is, for instance, which was not said yesterday, is that we also like to look at nucleons, so nuclei, where you have protons and neutrons, but instead of having a proton and neutron, you put another hadron in there, another baryon, which have strangeness in there, a strange quark. These are called hypernuclei. This is also a dimension which goes in this direction. So extending the nuclear chart to even going to very extreme kind of particles, right? So this is the philosophy what we are trying to do here at FAIR, looking at exotic matter to learn something about the underlying thing. Now we have facilities for that, right? This is FAIR, this is of course you have seen it before, this is GSI, this is how FAIR should look like, right? The CIS 100 ring, and then all kinds of caves and experimental facilities. Now if you look at hadron physics, this is now my interest, there are a couple of experiments being planned, hopefully in the future. The so-called PANDA experiment, which uses antiproton, which are stored in a ring, hitting a proton target coming from a pellet target or whatever, with a detector around it. This is a typical high-energy kind of detector, this onion shell kind of detector. You collide antiprotons and protons, you generate, for instance, this weird matter. You look at their decay, and the decay products you measure with a whole set of detectors and with a variety of detectors with many kind of sensors, and each sensor has its own kind of capability to detect a particular type of particle, their energy, their momentum, and so on and so forth, right? So you see these kind of complex kind of detectors. Now another one is, for instance, the CBM detector, the compressed baryonic matter detector, used primarily for heavy ion reactions, but also here one can do hadron physics as well. It's a different type of detector. It's not in the storage ring, you come with heavy ion or proton beams and you hit their particular target, and you're looking at also here some kind of modular kind of detector, but in principle a very similar kind of concept. Now this is the future. We also have an experiment which I guess this afternoon you will see that setup. It's called the Hades detector. This is primarily designed for precision dilepton spectroscopy, if you want. It has a beautiful magnetic field, being able to identify and reconstruct E plus, E minus pairs, but it also does many more. There's the Hades experiment which we are using today to do these kind of experiments. And then of course we also have another important thing, which is a green IT cube. We also have our own HPC center, which is again something very important. One always forgets about it, one thinks about its detectors, but this will become over the years more and more important. Why? Because we are producing more and more data over the years with higher and higher rates. Just to give you some feeling, once FAIR is running, we will produce, this will store in the order of 35 petabytes per year. We'll have about 300,000 cores. 100,000 cores will be also distributed in other facilities. In the order of 500 GPUs. So this is really a big facility which is supporting the data flow, the data analysis of these kind of large experiments, right? So this is the facility. This is what we are working on. Okay, let me give you some illustrative case, right? So some example. So also now getting closer to, what kind of challenges we have. Well, there are particles which have been discovered, for instance at CERN, or in China, and E plus, E minus colliders, which are weird. They're extremely weird. They also have a name. They call it the XYZ hadrons. They don't know what it is, so that's why they call it XYZ, right? But that was about a decade ago. There were, maybe you saw it also in the news. This is, I think, in the order of 10 years ago, 2013 to 2015. There were many of these kind of particles detected at all kinds of facilities in the world. The XYZ discoveries, right? Now we believe, or we hope, that these particles are these well-known or well-expected exotic particles made out of 4 quarks or made out of 5 quarks, called the tetraquarks and the pentaquarks, but we don't know it yet. There is no ambiguity. There are a lot of questions whether the things that we observe in these experiments are really somehow pointing out to these kind of particular states. So how do you figure out? Well, what you have to do is actually try to measure their composition, to do precision studies, measure their masses very precisely. This is one of the keys. Measure the mass uncertainty, the lifetime very precisely, which we then use in order to really confirm or deny, if you want, that these are the particles which people are looking for, right? This is something which we like to do in Panda. Okay, so how do you do that? Well, you need precision, and this is exactly what we do at FAIR. We have precision experiments. Precision means two things. Once you design an experiment which have an excellent kind of resolution, think about mass resolution, and on the other hand also produces abundantly statistics. If you don't see anything, of course, also it's useless, right? Okay, so how do you do that in this particular example? Well, mass measurements is an important theme also at FAIR. With the storage ranks, we have storage rank, we'll be able to get mass resolution in the order of 10 to the minus 5. So you can do a very precise mass measurements of, for instance, this X, Y, Z states, right? Statistics, well, that means you have to design a detector which can cope with huge rates. Why? Because these states here, what we're looking at, they have a very small probability of being created. We express it in terms of cross-sections. If you are known it must have a sensitivity of less than a nanobar. So you mean high beam intensities and the detector capability with high efficiencies, high acceptance, and so on and so forth. Right? So this is something which essentially one is trying to focus on. Now, this is the HESR ring, the high energy storage ring. This is meant to collect antiprotons. So this is a picture of the whole setup here. Of course, this is still future. We're talking about 2030 something, right? This is the Panda detector. So the antiprotons are injected here, and they are cooled. They are cooled. We already had yesterday about this concept of stochastic cooling, and this stochastic cooling is the key in these kind of things. And this is also why we like these kind of storage rings, because it allows us to actually have a very well-defined momentum of the antiprotons. This is a key, right? And that is by stochastic cooling. Yesterday it was already explained nicely, and it was also said it has actually a Dutch contribution. Simon van der Meer got a Nobel Prize for this kind of invention, right? And that gave to the rise to the discovery of the weak charge particle, the weak force carries, the W's and Z at CERN, right? So that is together with Rubia. So this is really a key element, something which was already known in the 80s as techniques, but now we're really going to use it to do precision mass measurements by using this precision momentum of the antiprotons, right? So this is the reaction. You hit an antiproton, well-known momentum on the proton target, no momentum. You create whatever exotic objects and you look at the decay products, right? And what you can do, for instance, if you roughly know where the mass of this particle is, you can do a scanning with a very precise beam, with a very low, with a very good resolution. You can scan, and at some point you hope to see a particular peak. In this peak position and also the width you can use to determine the properties of these particular exotic states, right? That's precision. This is one thing. The other thing is statistics. And now we come to problems. Now we come to data problems, if you want. Now the statistics, the problem is that the probability of creating these exotic particles is very small. This shows you essentially the probability, we phrase it in cross-sections, of proton-antiproton reactions. Most of the proton-antiproton reactions generate something completely garbage we don't really care about. This is essentially sitting there. This is how these are just some elastic or some particular processes. And 1 out of the 10 million kind of events we expect to produce these kind of particles. Right? So this is a challenge. So we have to somehow, first of all, want to generate many of these things. Right? That means we need a high intensity beam, right? And then we also have to be able to suppress the background. We get a lot of garbage, if you want, and have to fish out these particular events massively, right, out of this whole thing. This is the challenge. This is exactly where technology, computing technology, comes into play, right? Okay, this is the data processing scheme. So we have physics, some interaction, creating these exotic particles. Of course, we have a detector. This is actually the Alice detector, but it doesn't matter. I like this one, this picture. And then, of course, what you do is you do feature extraction on front-end electronics. You extract, for instance, the energy from a certain sensor, or you determine the tracks of a tracking detector. You extract that information. You do online computing to also try to reconstruct the whole event topology. Right, that's what you want to do. Then hopefully, well, probably most likely you also need some distributed computing because you cannot have the full resources here, but you also need to couple it to other facilities in the world. And then hopefully at some point you have a PhD student or a postdoc who is able, after all data analysis, to extract from particular spectra, if you want, some exotic features, some exotic particles, right? And you have a discovery. And of course, this whole process, well, that takes, of course, years to somehow get to this particular point. So this is all computing. This is all computers, all data processing. So the data processing over the years has become more and more important. There's also more, of course, detector control, that's also data processing, and also data management. If you produce a lot of data and you have to keep track of it and manage it, well, you have to also spend a lot of time and effort to have also a nice data management system, keeping also to the so-called FAIR principles, findable, accessible, interoperable, reusable, all these kind of things, right? So that is also a thing. And then on top of that, you also need a lot of Monte Carlo simulation. You also have to simulate, you have to make a simulation of your whole experiment. First of all, to design the experiment, to make sure that you have the right detectors at the right locations and whatever more to do your physics, right? That's what we are doing basically now in preparation, right? For that you have a model of your detector, a lot of computation time using Monte Carlo, but also during the analysis itself, you need some particular device which you use to optimize your analysis strategies, to use to get the efficiencies of the experiment, and so on and so forth. Right? So this is also a huge computational effort. Right? So the whole thing is only about computing, if you want, nowadays. Right? Okay, so let me just focus a little bit on these three items. This is me in 1998. I did my PhD in the University of Groningen. We had also a little accelerator, a cyclotron, called Agor, actually a French device. Doing quite nicely. Much lower energies, this is with protons up to about 200 MeV or so. So these are low energies. But at that time, you know, things were different, right? We're talking about 1998. So let me show you how, roughly in one picture, how the data processing at that time went. So this is how it looks like, a typical experiment. The data acquisition was actually very simple. Was very simple. You had about in the order of 500 detectors. These were actually barium fluoride detectors. It was photon detectors. You measure the energy. We also have some wire chambers, getting some information out, right? And those information, well, you had discriminators, right? And those discriminators, the logic signals you used to build a trigger. And in those times, you know, you were happy if you could make a coincidence between a couple of detectors. Maybe have some memory logic unit to do it a little bit smarter. But you had a simple kind of trigger on a LIMO cable. And that LIMO cable, then you connected to ADCs and TDCs to wake them up, to start integrating, charge integrating and stopping the time, whatever, of the signals which are coming. Right? And the signals you delayed. You need some time because the trigger meter was like 500 nanoseconds or so. So you need to delay it. So you put a lot of cables there, right? So that was all cables, pulling cables. This particular electronics, which was came in via me, you did not put close to the detector. No, you were scary. No. You put everything outside the experimental hole, right? Because you are afraid that during the beam you cannot just go in, right? So, but you still want to play with things, right? So but it all has changed. But this was the time when I did my PhD. And the nice thing is a PhD, I worked on all the facets of this experiment, building the setup, building the data acquisition, making the analysis scheme, and so on and so forth. But nowadays the scales are completely different. That you cannot do anymore with 1 or 2 graduate students to set up the whole experiment. You need a whole collaboration, right? Okay, but that was the late 90s, right? Okay, the picture, reaction rate against event size. So this gives you somehow the data rates over the years from various experiments. LSC, by the way, this is the LSC experiment. This is run 1, so these are nowadays they also moved up here enormously. So I have to update at some point the spectrum. But here I was in 1998, 1 megabytes per second or so. Typically the event rate, peanuts nowadays, right? Then okay, I got involved in BESS 3, nuclear nuclide in China. Okay, already moved up here, right? And then HADES, this is what we're doing here now, in the order of it can go up to 10 kilohertz or so, typically. And here we want to be in 2032, for instance, with the Panda experiment, right? So we're breaking, this is all log scale, right? Just look at this is all log scale what we're dealing with. So the whole processing becomes way more challenging, right? Over the years. Yes, and yeah, we cannot make use of, well, there is a Moore's law, absolutely, right? I mean, the number of transistors is also growing, double every year. But the clock frequency is basically has stalled already when I did my PhD in 2000 or so, right? And already at that time, you know, double core processors came out, and you know, things are changing. There was a whole paradigm shift already taking place. But it also means that the software one has developed in the 90s, yeah, well, has to be adapted, right? It was a whole paradigm shift in data processing as well, right? Okay, so what is nowadays the picture of how to analyze the data? And nowadays the buzzword is free streaming online data processing. You don't use a hardware trigger anymore. You cannot use a hardware trigger anymore. Your detectors, they produce data autonomously, producing in buffers as a front-end electronics, creating buffers. And then on different stages, you know, some particular compute nodes where data is being collected, where some first level analysis is being done. You combine by data concentrators the data, and at some point, at some particular level, after already some pre-processing, you start making what we call event selection. You already almost reconstruct the whole event, what you normally in the past have done offline, you do now online. And then you start deciding, hey, wait a minute, this looks like a tetracore candidate, let's keep this event, right? No trigger involved anymore. This is now the whole change what you do. So that means essentially that that online and offline computing are merging together, right? So this is another picture. So we have 10 megahertz interaction rate with Panda, right? And then we only will be able to store about 10,000 10 to the 4 events per second to make it all manageable. But it means that online we have to do all these kind of algorithms, track finding, feature extraction, vertex fitting, particle identification, kinematic reconstruction, all have to be done online in situ, right? This is the thing what we are essentially dealing with. So in other words, online and offline in the upcoming experiments will actually merge, which also means that there's a lot of pressure on doing online computing, right? Online, I mean, after all, I mean, now with offline computing, well, you can, you know, you take some data with some simple trigger, and offline you can make a mistake and you rerun the data again. No, you might lose all your data if you don't do it properly during the experiment, right? So this is now really something which is coming online. Now, how do you tackle this thing? Well, there's a buzzword which you hear now constantly. It's called you have to federate. Federation, that's important. Of course, if you build a collaboration, then there's also federation. I think you also guys are all federating for this GNU radio, right? So federation is something which is extremely important. Also in our business, federation, hardware and software. Federation in on and offline computer. Federation in distributed computing. Federation in anything that has to do with computing, right? This is now the thing which one has to follow. Okay. Let's go to software design. I'm getting now closer to also your business here. A couple of cultural facts, how software is being designed or being used in our communities, right? First of all, people like to see fast progress. So if you build a framework and you give it to your collaboration, they want to see very quick results. It might not be perfect result, but they want to see results, right? They're not going to wait for 1 or 2 years. So the learning curve should be actually the learning curve should be steep to be technically correct in wording. I think often people use it in the wrong way, but you have to get knowledge very fast, right? So that's the thing. Now this is something which I was actually computing coordinator in Panda for some time, and actually we killed the whole framework here, an old framework, because it didn't connect to this particular item here, right? There's no distinction between the users and developers. Developers are sometimes users, you know, because they know a little bit how to program, they become a developer, right? They do something, right? This is somehow the thing we don't have really people, often people really dedicated. Yeah, there are always a small IT department here where they're dedicated, but in the collaborations, no, there are no, let's say, engineers, software engineers. Hardware engineers you find, but software engineers don't exist. Code is then also often developed by people who do their PhD or postdocs. And their PhD is about physics. If you come with a PhD there and say, yeah, I spent my 4 or 3 years on doing code design, you will not get your PhD degree. Yeah, you can do it aside, but it's often then something, you know, difficult. But I think it's changing, by the way, but this is certainly something which we worry about. Yeah, and reinventing the wheel is unfortunately a very common practice. That is probably what you see in any kind of software world over there for some reasons. To be stubborn, I know it better how to do it, but sometimes also lacking information, right? And it's an evolutionary kind of process, right? So this is not, to build something by design and then deploy it and everyone is happy. No, you start with something and then you let the users play around with it. You get some feedback. Of course, you also need the whole communication system around it. And you progress in building your particular software framework, right? And lastly, in a certain point, is the recognition of software R&D still lags behind other R&D. So hardware R&D, yeah, that you can publish, yeah, that's a good part of your PhD, but software R&D, that's a side issue. Thank God it's changing. There's even nowadays a journal, which I'm actually one in the editorial board of that, Computing and Software and Big Science. So the recognition is getting there, right? But not yet fully, right? Okay, so what is important then in order to still be able to realize something? Well, the buzzword, of course, is frameworks. I think you're well also very familiar with that particular concept because, yeah, then you have also a controlled way that the whole user community is using the same thing. Productivity boost, accessibility, scalability, flexibility, blah, blah, blah. All these points, yes, you need a good framework. You need a good software framework. So I guess I don't have to explain it to you, right? Because you also deal with this. But the real question is always how to make a framework actually successful. How do you make sure that it's actually being used? How do you ensure that your collaboration actually is nicely and livid, and that the lifetime of your software is also holding for a very long time, right? That's of course the point. That's really what's making a framework work or not work, right? Okay, there's a good examples over there. This is root. I also understand today that GNU Radio is also making use of root functionalities, right? Now this is a framework already there since 1996. So again, when I was doing a PhD, I just moved from POR. That was more a Fortran-based kind of framework, also coming from CERN, by the way. And we move into this object-oriented thing, which was called root. In my time, I didn't dare to touch it at that moment, but when I came a postdoc later, yes, it became a standard, right? That was a successor, the successor of POR, the physics analysis workstation. And that is now has a huge community, right? It's very much concentrated on scientific data, storage, processing, visualization, analysis, statistical tools, very broad, also even now a machine learning tools there. An interactive interpreter, beautiful. People have done a low threshold to immediately do something with it. Huge community beyond the high energy physics community, right? If you look all the community, hadron physics, nuclear physics, heavy ion physics, particle physics, other communities making use of this particular framework. And of course also can run it on many, many kind of platforms, right? Okay, now based on root, there's also a local success story. This is called Fair Root. This was from the IT department here. I see Florian over there is also part of the team maintaining and developing the so-called Fair Root kind of framework. This is a framework since 2003. This was more or less when, in this case, CBM, I think they started using this. They wanted to have a framework where they can do simulations, realistic Monte Carlo simulations to design their particular tech. That was the start of it, right? And they want to have something which immediately gives you very fast some results, right? Instead of that they have to somehow figure out how to use AR and how to do this and this. No, in that case, the IT department here came with a nice framework, a modular kind of framework, of course making use of the root library functionality and also making use of all kinds of transport models to do this Monte Carlo simulation. At that moment, there was a Gen 3 transition to Gen 4. They do something smart. They use virtual Monte Carlo where you can easily switch from one model to the other, right? And then they also have a task kind of mechanism which allows then the users to easily set up their simulation framework and later on their analysis framework with all kinds of, nice functionality. And this is now a very big success story. It's not only CBM is using this, but also Panda later used this, and R3B, these are nuclear physics experiment users, and also outside FAIR, people have started using these kind of successful frameworks. So that is a typical success story of what I call federated kind of computing. It even has some kind of spin-off. So Fair Root, also people at Alice, that's CERN. I'm now moving towards CERN now, Alice. Alice, by the way, also GSI is involved in the Alice experiments. So there was already some kind of natural connection between the Alice community and the Fair community. But also on the software, there was some kind of spin-off, some federated kind of spin-off going on. And there, for instance, Alice is already a running experiment, right? They're taking data, it's a heavy ion experiment. They look at lead-on-lead collisions. at very high energies, much higher energy than at fair, they were running, right? And they already have a certain framework that's called the O2 framework. That's the online-offline framework. And they already, at that moment, start realizing, they're of course already way ahead in that sense, because they have a running experiment, that you need somehow to merge the online and offline, couple it to your data acquisition system. And they were also actually at the stage to upgrade their detector to go to higher intensities. Just to give you some feeling about, in 2021, they start preparing for run 3, which already have taken place, which produces, data in the order of 3.5 terabytes per second, right? So these are huge, these are really large data streams, waterfalls of data. They have to do with this, right? They have to do with it. The reason was they upgraded their time projection chamber, which has to do with these particular higher rates. And at the same time, FAIR, that's here, we were preparing these experiments for CBM and Panda and NuStar and so on and so forth. We already also thought about this concurrency problems which we have to deal with, right? And of course we also like to see this merging of this online and offline. So that is of course in a natural kind of combination where also the both types of these are the 3 experiments, one at FAIR for the future, CBM, Panda, also with huge data range, and then with Alice, right? So the natural thing is trying to see whether we can combine our knowledge, and there came a new product, it's called Alpha. I guess it means Alice Fair, with a combined kind of framework to tackle these concurrency problems for data acquisition, to have this online data acquisition somehow being enabled. And the trick here, I will not go too much into detail, is that they actually developed a so-called FAIR message passing software framework, which is based upon a very old model. It's called the actor model. This is already from 1973, right? Based on these simple kind of state machines, which gets a message, passes it, do something and passes a message or kill themselves or create something, right? I mean, so it's basically another kind of layer on top of your internet, which allows this message passing and which allows to build up in a scalable way a whole network of processes running in parallel, dealing with this concurrency issue, right? And the nice thing about it is fault tolerant. If one of these messages, if one of these devices here gets killed for whatever reason, it still survives, right? I mean, those kind of things are very important. And it's very scalable. It has, of course, a communication layer, something which is also familiar to you, 0MQ, dealing with shared memory, also being able to communicate over libfabric. So that's the product, and that actually gave successes. It gave successes. For instance, this is now the picture from Alice, where now there's a transport layer. This FairMQ, this alpha framework, has been installed on top of their data model and on top of their data processing layer. This is where the user sees things, right? And this is really hidden by the users. But at least it seems to work. They indeed have now a whole nice data acquisition system where they could merge the off and online kind of activities, getting these 3.5 terabytes per second of data being pre-processed using this kind of layer over there, 230, and then also offline using the same kind of algorithm, the same kind of system, doing a recalibration, eventually dealing to a permanent storage, right? So that seems to be very successful, but also the whole kind of framework is being used for CBM. CBM is not a running experiment, but we have a mini CBM where we have, a set of detectors, small set of detectors, which will also be used for a mini CBM, putting together in beam. And also one of the things, of course, is testing the detectors and whatever more. But also an important element, actually the most important element, is to test this online data processing, using now also these FairMQ kind of bases, right? And that is also something which has turned out to be very successful, where you have under the triggerless front-end electronic kind of scheme, using now the first level event selection, also involving the green IT cube, the whole kind of line, the whole kind of event processing has now been demonstrated with such a mini CBM, also giving rise to even some particular physics peaks over there, which I will not go into detail. Okay, so that's one thing, right? Federation. Federation is an important kind of element. The other important element is go outside your box. Try to get your algorithms smarter, more efficient, and so on and so forth. So this is a thing which I personally was very much interested in, to see actually how we can actually improve our algorithms to get things a little bit smarter, and hopefully also deploy it to online computing. Right? So that is a thing which I thought of. And of course, what you have to do then is to look outside your boundary boxes and communicate with other kind of groups in the world, like for instance with astronomers, or like for instance people from computing vision, or people from biology, right, where they also develop algorithms, smart algorithms, and learn from them and see how we can also use it for our hadron physics or high energy physics kind of experiments, right? Now the topics over there, computing vision, machine learning and AI, they have of course becoming an enormous kind of boost, as you can imagine, over the past years. And this is also, I think, looks extremely promising. Okay, why do I think it's promising? Well, first of all, it has become very trendy. Extremely. This is, if you look up the word machine learning, artificial intelligence, deep learning, you do a search over there in Zenodo, for instance, and you try to get the number of articles which mention those kind of words over there, you will see that over the years, somewhere about 5 years ago, it games exploded. Explode. Now you might think, yeah, maybe people have just published more. Well, also the fraction of those articles have exploded as well, right? So there seems to be something from the past 5 years which made this very interesting. And this is certainly not my articles here, right? This is the community, different one from physics, from chemistry, material science. There's a whole kind of community is now seeing how they can use, and that machine learning and AI becomes more and more important to do their kind of research, right? So it seems to be a boost going on, right? Now the question is there some wave again, like we have in the 90s, right? There was also some particular wave on this. Well, that's still the question, but certainly over the past 5 years, it has been boosted up, right? Another boost here, AI. There's also in the we are living in the state of Hesia, and there are all kinds of universities. They also get funding from the state, and they put things together in the topic AI, right? And they also now are trying to lobby, big lobby groups, trying to get funding on this particular thing. And also here, GSI is involved. We rent out part of our Green IT Cube to build an innovation lab, AI innovation lab, right? So there's also here certainly a new trend going on, and we are also somehow involved, right? Also on the German level, this is on the state level. On the German level as well, digitization in Germany is also a word nowadays. It's, if you realize that people in Germany are still using fax machines, I guess it's not a big surprise that they worry about digitization, right? But also here in Germany, there's a big lobby towards German funding agencies called BMBF, trying to get funding for computing-related aspects, where AI and machine learning becomes also an important element. There's a whole kind of consortium being created, a bottom-up consortium. They organize all kinds of schools and workshops to train the trainers, but also to train young researchers to learn about deep learning, to learn about the basic concept, and so on and so forth. So this is a whole kind of thing which you now see over the past 5 years boosting up. And also towards the EU, the European funding agencies. We also have to there trigger and see what we can release over there. And there's also a new consortium being built up. It's called the EU CAF. This is actually fundamental AI for fundamental kind of physics, which recently has started to, they had actually an opening workshop in Amsterdam. And that is also meant to get interest to AI from the various communities, including nuclear physics, and lobby this to the EU, right? So there's a lot of trendy things going on from the publication point of view, from also the lobbying kind of view related to machine learning and AI. So what is really going on here in the past five years? Well, first of all, if you look at AI, and you look at perceptron, the concept of a perceptron, right now I'm talking about deep learning over there, is already from 1943. Right? So the mathematical idea of representing let's say here, a piece of brain there, right, as a perceptron in a mathematical way, it's from 1943. So that's quite a long time ago, right? So this is, in that sense, nothing new, right? What is really new is, of course, the big tech people coming with large language models, right? Transformers has become extremely important, right? And they are also very successful. I mean, just this is over the past 5 years. You see here ChatGPT-4, right, with the order of 117 trillion of parameters, typically, right, and that has been grown exponentially. It has been grown exponentially, and nowadays have these very powerful machines. And that all happens roughly about 5 years ago. And this is somehow also picking up from the scientific communities. Right? This is the reason why the things are being boosted. Now let me put it somehow into a certain concept. Let me take this particular picture where I show you the number of parameters of these language models, right, these transformers, over the years. And I'll put it with respective to the number of synapses in brains of mammals over the years. This is actually the so-called Schwarz plot, showing now the evolution of mammals over the years. Right, so here we have the mouse. It's also divided into a different thing. We have a cat, chimpanzee, and there we have our humans. The number of synapses is in the order of 150 trillion. ChatGPT, 170 trillion. The growth, look at the growth. The growth here, this is red line. This is what nature does, what evolution does, if you want, right? The growth in AI is this blue line over there. It goes at 10 to the, both are growing exponentially, yes, but the AI is growing actually with a factor 10 to the 6 larger than that. Now you might think, okay, maybe the software in our brains is way more smarter at the moment than I could be, but the question is, will that change, right? So certainly it is clear that also humans will have to also use AI to get more information out and rely on what they get and to trust them, right? That's the whole thing what you have. And people might also say, yeah, but you know, humans might also get smarter, you know, this is maybe a little bit overdone. Well, think about a cat, right? A cat is over there, about 70 trillion synapses or so. You will never be able to learn a cat how to do chess, right? So there is a limit. Also, humans has a certain limit. But in principle, AI, or at least the blue line over there, in principle has no limits, right? So this is something to think about. I think this is, for me, it really dawned into me that one also has to realize where this particular boost comes from. And of course, one can also then get scared and all these kind of things. But this is a reality. AI will help us, and AI will actually be able to provide information which we are not able to do or get. And they have to dumb it down for us in order to understand it. This is how the reality will look like in the future, at least if you trust these kind of particular pictures, right? Okay, now of course getting a little bit into basics. Machine learning applications, right? I mean, what are we doing now? I mean, machine learning is also something which is not very new, right? We're all using it. If I ask, for instance, a student which comes and say, look, I mean, do you know machine learning? Or he or she says, no, I never use machine learning. Well, then I say, yeah, but hang on. Did you ever fit a spectrum, like a least chi-square fit or whatever from data? It says, yes, well, you did machine learning. Ah, that's machine learning, right? Using algorithms to get knowledge out of data. That's a fit. Right? It's machine learning. Of course, you know, this is a simple one-dimensional kind of thing if you want. Of course, we can go to much more interesting feature spaces. Clearly, right? This is now what we're doing. But we're trusting this already, right? Classification, for instance, right? Classification. If you want to do tracking, doing hash transformations or doing Riemann filters or doing all kinds of things. Yeah, we are certainly trusting the result at some point, right? Or think about clustering. That's certainly some very common theme if you look at clusters of an electromagnetic calorimeter. Yeah, there are algorithms that do it very smartly and very efficiently, like for instance a mean shift or based on some neighboring kind of relations. Or fitting. Now we nowadays do very fitting on complex data, having kind of physics constraints to improve resolutions and all these kind of things. It's very common. If you write this in an article, nobody will argue for these things anymore. If you use your analysis, a boosted decision tree to do classification of signal background. 10 years ago, people were not trusted, but nowadays, there's no issue. You can do these kind of things. People believe what you're doing, right? Now, the question is, can we go one step further, right? Can we actually go to the next level? And this is now where people are thinking out at the moment, the promise for the future. Detector responses, we're using these Monte Carlo simulations, you know, using these tracking, you know, these are very computationally expensive things, right? But nowadays you also have gun networks which can produce images for you. Why not try to use those kind of things to model the detector response? It's way more efficient. You can save a lot of computational time. Assist in detector design. We have complex detectors, millions of parameters and sensors. And we like to design an experiment, optimize a certain physics. This is an optimization problem in very high dimensions. Something where you can use AI for, right, or machine learning. Real-time event selection. Anomaly detection, data mining, experiment operations, all these kind of things will over the years become more and more important in our particular field. Even the word foundation models is nowadays falling, although I still don't really understand what it is, but it doesn't matter. There is all kinds of new things coming here online. And is it all hype? Well, of course, I always say, well, as long as you keep this particular rule, is don't use a cannon to kill a fly, I think this is fine. Right? Okay, let me give you 2 examples, and then I also close up here. First of all, now you see already a self-driving car here, right? That's very clear. Now you might also, I always thought, okay, I mean, self-driving cars, this is also something which will come at some point. Of course, there's all kinds of resistance because people also like to drive themselves. But then I also thought, yeah, wait a minute, if you have an experiment which is very complex, why not consider also a self-driving experiment in a very long run? What is wrong with this? Actually, I think you need this. Look at these detectors. They are very complex, right? Look at the fact that that in the future, in the near future, we will have beams at extremely high range on the very harsh environment. These are heavy ion beams. There's a lot of radiation going on, right? So stability is becoming very important. We want to do this in situ event reconstruction. So we have to make sure that our calibrations are correct, always correct. Nowadays, we can do, in the old experiment, you could do the calibration offline, right? And you update your data and whatever more. But now you have to do all these things during data taking. Okay, so maybe one has to rethink the whole business here. Cost, right? I mean, it's very high. I mean, this beam time is very expensive. Human resources are very expensive. If your detector system in your experiment becomes more and more complex, well, you don't get more beam time, right? You don't get more people. Forget about this, right? So you have to do something smarter. And of course, if you have a PhD and a postdoc, you need also to publish. They have to finish their project in 3 years. If you have a complex detectors and you have this PhD student spending 3 or 4 years to calibrate the data, you can do it now. The complexity is small, so now they have to spend half a year to a year on calibration. But with such a detector in such an environment, it will not work anymore, right? So these things, I think, are underestimated in the experiment. Accelerated people already understood this. They already understood, to make stable beams, you need some AI there. That is there, but experiments are lacking way behind here. Okay, let me give you some feeling for this. And I go to an experiment which we are running these days. It's called the Hades experiment at Fair Phase 0. So when I moved from Groningen to Germany, 1 month later I was involved in this experiment. There was an experiment in 2022, yes, 2022. Proton runs and some hadron physics experiment. I was really enthusiastic. Yes, we have to do it. Now, this is an interesting detector. It's a detector which is, it's somehow in between the past and in the future, right? It's already a very complex detector. It already has quite a lot of sensors, if you want. It's also complicated, many types of sensors. It also has a data acquisition, which is still trigger-based. There's still a physical trigger, right? But still, the number of detectors, their front-end electronics is already getting very smart to a certain extent. And also the event rates, typically up to 20 kilohertz with 400 megabytes per second. These are reasonable large numbers. So it's getting to a certain limit where things already, you're stretching it already, right? Now, to give you a feeling that we're stretching it, so this is a picture of a beam time in 2022. This shows you here the operation, the shift. You had 2 who have to be in the counting room. This was, by the way, during COVID time, so you see people had a mask. So we could not have more than 2 people in the room, was not allowed. But of course, you see always, this was at night on Sunday or whatever, right? You see always like 2 or 3 or 4 people in the counting room. And then also online, there were about 10 or 20 more, all monitoring the individual detectors. Looking at spectra, if something wrong, call the people on shift. And the people on the shift don't know what to do, data acquisition crashes, call somebody else, this and that, right? There was a big operation going on in order to get things running. Now, this is still doable. This is still something doable on this scale. But now imagine you have a CBM experiment where the rates go up by orders of magnitude. Complexity goes up by orders of magnitude. This will be a killing fact. You have to do something smarter on this level, right? You cannot rely fully on the human resources to do all these kind of things, right? So this becomes really a panic situation. This will be somebody on shift, right? So I hope then that, one also can have some rest as a human, right? And hopefully then also have, let's say, an AI kind of system where you essentially, conceptually plug in the environmental variables, the beam parameters, the beam settings, the beam conditions, maybe even some Monte Carlo data. So you have also a model of your detector in there, right? And then, hopefully during your experiment, pushes out calibration constants over the detector on the fly, right, on the fly. And even if you're really daring, be able to change actually the high voltage and settings of your experiment. Let the system do it, right? Now, if you show this to people at Harvard, they think, no, we will not do it. So this is certainly a conservative kind of theme behind it. But I think this is really needed also for the future. Okay, now of course we have some pilot experiments. So this is actually a graduate student of mine who's at the moment in Warsaw at the Harvard meeting. There's a Harvard meeting going on. And he already started looking into AI or machine learning, some neural networks, some convolution kind of neural networks, to see whether one can do these kind of things, right? So what he did is he take the data from 2022, rewind it back, right? Picked one particular detector, in this case the drift chambers, so they are used for tracking particles, right? You bend the particle in magnetic field, you get the tracks of that and you get the momentum out. But these things are also being used to do particle identification. You measure the energy losses. By time over threshold of pulses, you measure the energy losses. But you know, the gas is a gas system, so you're very sensitive to environmental variables, right? So your energy loss, it's called the EDX, will change over time, not because of physics, but because of pressure in the gas and so on and so forth, right? Now the question is, can we somehow build a system which spits out these calibration constants online? Of course, we didn't do it for a running experiment. We did it. We replayed back an old experiment, but see whether we can do it, right? And it seems to be very successful. He uses a long short-term memory network and a graph embedded in a graph convolutional network. And indeed, he showed that this is essentially the EDX over time. So this is a nominal value, and then because of calibration changes, it starts fluctuating because of mostly of these environmental. This is basically the main feature factor which is relevant. And here, this is the training, and this is, for instance, the red with respect to blue. Blue is the target. This is what it really is, if you want, and the red one is essentially what the system predicts over time. So yes, in principle, very smooth, you can do this kind of thing. Let me give you another example. And for that example, this is my last example, I go to Japan with you. This is our colleagues in Japan, also have an accelerator. It's called the Japan Proton Accelerator Research Complex. Somewhere over there, not so far away from Tokyo. They are colleagues. If you go outside GSI, you probably can see it also from here. You see this kind of little thing which pointing where other facilities are. This is where it is, about 9,000 kilometers away, JPAC. This is one of our colleagues, right? So also our friends there also doing experiments here. We have a collaboration between each other, right? But they have also an interesting experiment. And one of the experiments what they're using, this is Taka Saito. He's working half-time if you want at GSI and half-time also in Japan. He is crazy about hypernuclei. So trying to discover nuclei where you replace the nucleons by a hyperon, so strangeness in there, so exotic nuclear matter. On the third chart, right, I showed you in the beginning, right? So how can you detect those kind of things? Right? There are only 5 events have been seen on the double hypernuclei, and he wants to see many more of them. Now he has a setup for that, and he uses a technique which is already from 1905. I think Rutherford used it, and that is called nuclear emulsion. These are emulsion plates. What he has a kaon beam, hits some particular target, and there are particular particles called cascades or so. They actually interact with emulsion plates. These are photographic plates. So they do an experiment, have a series of emulsion plates. They shoot a beam for some time on it, right? They stop the beam, they take the emulsion plates out, and these are photographic plates, and they develop it and look at images, right? So what happens if you go with a charged particle through these material over there, you have silver halide crystals, and they actually start getting bigger. And if you develop it, then you can see that very nicely. This is how it looks like. It's like bubble chambers, right? More or less, sort of, right? But this is now with photographic plates. Now the nice thing is that you have an excellent position resolution. It's better than a micrometer. So there's no other way with tracking detector which we have here. These drift chambers and TPCs, you will not get such a high precision as given here. Right? So that is certainly one thing. So here you see, for instance, all these tracks. These little dots, these are the beam punching through, right? But you see also these little stripes here. And these little stripes here come from a decay of something. And of course, what you're looking for is a decay of this exotic hypernuclei, right? This is what you're trying to do, right? But you have to analyze these images. So what you do is you take these many emulsion plates out, you build a microscope, right? And you make images, and you do some algorithms to try to find patterns in your data, which might look to the event what you're looking for, right? This is the idea. Now these experiments are already pretty modern. They run for a long time, and if you use now the standard techniques, the standard algorithm, and the standard way of actually also where humans often has to actually look at things and check things, it will take about 560 years to analyze the data what they took. They took about 100 petabytes of images generated from these emulsion kind of plates, right? 560 years, well, that you can forget about. If you ask a funding agency to get a delivery result after 570 years, they will say crazy, right? So you have to do something else, right? And he, of course, came with the idea, yeah, why not using, in this case, mask R CNN, so convolutional neural networks, using mask R, so these are region-selected CNN kind of things, and masking to get faster events out. And that turns out to be very nicely. He also used a GNU network to produce simulated data, which actually looks like real data. And it turns out, indeed, he can identify certain patterns. This is alpha part, it's a calibration parameters. But indeed, it turns out it works very nicely. And he can actually calculate it. He can reduce from 560 years to 3 years kind of analysis. Now it becomes doable. Now people start happy. But you need to go to smarter kind of algorithms, right? Otherwise, you will not be able to do it. Okay, let me round up here. So, pushing the boundaries, femtoscale research with large-scale tech, that was somehow the title. Let me give you somehow the takeaways. Well, and hopefully then we can also have maybe a discussion about how we can connect with radio, GNU radio. So, a couple of takeaways. First of all, evolution of femtoscale research fundamentally depends on breakthroughs in computational technology. Computational things are becoming essential. And the developments over there are also becoming essential to be able to deal with the next generation of experiment. There's absolutely no doubt about. And I think this also has been very strongly being recognized. Now, most of our computing innovations actually are already based on stuff which were invented, concepts. Well, think about the Turing machine from 1938. This is actually the concept that you guys are also using, right? So all these concepts, actor models, Turing machines, all these things were already invented decades ago. But now we start using it massively in a kind of interesting environment. This is really what you see over. This is very interesting, right? Now, as I said, online computing has become smarter, online has become offline. This is a thing that we are now tackling somehow. And as I said, the application of machine learning, or AI, but also I didn't talk about open science, so one can also think about the ChatGPT for the data which you produce over there, for data management. That also has attracted a lot of attention over the past decade, so the past 5 years, right? That's really what you see, right? Unfortunately, okay, one thing is the interest is mostly driven by funding opportunities and by excitement, technological kind of excitement, right? And I have to say, this is more a critical item, is academic values. So the impact on scientific advances are yet underestimated by a large community, I have to say, but I'm sure it will be increasingly being recognized over the years. So that is something I think I personally believe is the case. Okay. GNU Radio, right? I started, well, first of all, GNU Radio, the integration and accelerate and ring activities at GSIFA, I think this is already there, right? I mean, this is beautiful. You have really a nice kind of collaboration, and you see some synergies, and you see the beautiful, right? There's no doubt about it. The question is, now large experiments, the thing that I present, are there things useful, maybe from both sides, where we can think about it? Do I have to believe the recommendation of ChatGPT? Question mark, right? To what level? What about the role of machine learning and AI? I don't know. Suggestions. So here I stop. I thank you, and I hope we can somehow have some discussion on these particular questions.
Any questions?
Suggestions?
I guess most people are still in awe about. You presented thank you very much for your talk, which is excellent. Thank you.
So thanks first of all for the great talk. When you showed the reduction of time from 560 years to 3 years in that example, how long and how did you do the training of the neural network?
Yeah, so the training is done on Monte Carlo. Actually, of course, you also will generate a lot of Monte Carlo data, right? So you have also a model of the reaction of the emulsion plates is being modeled. That is then actually being pushed to, well, first of all, I didn't do it, but this is of course in Japan. Use a gen, that is actually training using a gen kind of network, which then can create on the fly very fast images which are as realistic as possible as training. Right? So that is being done by a GAN kind of network kind of environments. So also there, deep learning is being used, not only to classify, do the inferences if you want, right, of the images, but also for the production of the image data. Monte Carlo simulations, producing something, you build a GAN network, then eventually making the pictures constantly, right? So that's the theme that is being used. The bottom line here, there's still 3 years, but you still have to do all kinds of mechanical activities, right? Still putting it, so that's really somehow, there's always a limiting factor, right? So there you have to realize.
So I'm mentally still a bit processing 75 minutes of Dan's talk, but you were mentioning the framework aspect of using things that others can then build on and think. And this kind of ties into it, because when I see someone having learned something, especially when they apply like GAN techniques, right, they will get what they asked for in the data, right? I ask my system to find the data that describes the statistical model, I assume, and if I then find exactly that, then in the classical system that would be kind of like result picking, right? I'm not doing an experiment to verify an hypothesis, but I do an experiment to find something that serves as hypothesis, and then I will find, yes, I can verify that because I just picked enough data to find something. So how does a large scientific group ensure that this does not happen? How do we ensure that when we're building models, be it like very classical, like I sit down with radio, I write a signal processing flow graph. How do I verify that my model of reality matches what I wanted to do? Or how do I verify that a complex model that I did not even design myself matches reality?
Yeah. Now, of course, you can also use the data itself, right? I mean, of course, there are a lot of, let's say, processes in these reactions which are pretty well known. So the modeling of this is very close. But of course, if you try to look something exotic, right, you don't want to explicitly put it into your frame, because you need to know it, right? But it's about the things which you have to filter out. The things which you have to know has to be modeled properly. Anything else on top of that is essentially an anomaly, right? So it's basically you try to filter out the things which you know. This is actually the concept.
Okay, but then you mentioned that you could use like something like the image generators for a experiment design problems,
yeah.
right?
Yeah.
So and this, of course, they are very much.
Yes, then you need a specific model that you have in mind to test it, right? That's correct. But yeah, but this is in principle also how science works, right? The same is with the Higgs discovery. It was postulated that there is a Higgs with a certain mass and a certain properties, and people try to look for it, right? So it is essentially also a scientific kind of way. And then indeed you train, you optimize your system to look for that particular thing. In this case also, I'm looking about theta quarks and pentaquarks. We already have found them. Right? It's not like we know roughly where they are. We know roughly what their properties are in that sense, right? But we didn't do a precision measurement of that. Yeah. This is the thing what we're doing now, right? So in that sense, if you optimize your detector still on something which other previous experiments have discovered, surprisingly, right? And then things. This is basically how it somehow works, right?
Yeah.
some kind of an iterative kind of way. I mean,
Okay, thanks.
Not really a question at all, but I just love the starting point. Like, what is the origin of mass? And then meanwhile, this whole, like, all of it. I like that part of the whole inquiry that leads to all of this questions, equipment, how would we know? How did it come together?
yeah,
And
this
the
is
example of the Higgs presenting like such a small fraction of the actual density. It's like,
Yeah.
okay, what is going on?
Okay, now I'm also being honest. I shoot myself in the foot. If you look at the mass in the universe, this mass, that fraction is also very small. We still have dark matter and dark energy, right? This is really the major question, to be very honest. But yeah, this concept indeed that you're triggered by something and then you have to build something all around it to realize that this is, of course, what is. I agree with you. This is the exciting element in that. Yeah.
I like the point that you made with root, because the things, because I mean, like I also had like a HAP background, but in terms of technology, both the people who write root and work behind it on a C++ level were closely collaborating, because they also want to get the compile time reflection and SIMD into the C++ standard, and they also have a similar problem with root as with GNU is like maintenance, because the code base is now more than 20-25 years old.
Yep.
And the question is like how to rejuvenate, how to modernize it and make it slimmer, more effective, because they have code base. Basically, high energy physics runs for 20-30 years looking at the data, so they have to make sure whatever they wrote in the 90s
Yes.
still can be written, read and processed today. How to keep that continuity, and that is the same problem. I mean,
Yeah, these are big time scales, yes. And so
Exactly.
I agree with you, yes.
I mean, coming back to the software side of things, and root is an excellent example of that. How can you, this is a completely different topic than the science side, but how do you ensure that when you develop something large, frameworky, that this converts into something that can be maintained for 20 years and that's kind of important to the GNU thing, because GNU in itself does not originate from a large research facility, right? How can you take this and keep it maintainable outside of something? I know that Ralph and I had been, in a lot of discussions on things like this is like, we cannot assume that the user will compile his own code. That will not happen. We need to have this kind of thing. How is there mechanisms in the large-scale scientific software design world where we say, okay, we're developing something for an in-house purpose, but we're making sure that this will, survive the PhD, survive the working group, survive the single experiment that might be running for 10 years, and be useful afterwards.
Yeah. Now, and of course, the organization and collaborations is more or less top-down, right? There's an organization, you decide on a certain framework, right? Of course, there's always a risk. I mean, sometimes a framework doesn't survive, right? That's correct. But the timescales indeed are very large, so the risk is that a PhD student has to change now the framework is very unlikely. Now, of course, what we are doing, to be very honest, we look at what the high energy physicists are doing now, right? This is certainly our guide. They have, to be very honest, they have the experience, right? They have the experience. They know how to make sure that the framework is modular enough to also cope with the developments which they are predicting, right? So we always try to connect to communities which certainly have experience already in this business. So that's why FAIR is using FAIR root, right? To be very honest. But maybe Florian is a real, maintainer of FAIR root. I'm sure he has a certain opinion about it.
Yeah, there one has to go to a little bit in history. So this, as Johan pointed out, started as a project for an experiment, a specific small experiment, and there were some clever people working on that, and they realized that it is a good idea to share also workload with other people. So they announced this project, and with Panda, then the second experiment located here at GSI joined, and this also shaped the experiment. And in the end, sorry, not the experiment, the software state, because now there was another customer with some slightly different needs, and so this has to be adapted. And then this was announced also in the community and on collaboration meetings and so on, and more people realized that this is maybe something which can help them, and so the community grows. So this is a community-driven project, and in the end, I think the real thing is that I would say GSI and FAIR see the need that this is supported and put some manpower on that, because otherwise you cannot do that. Because the experiment, so if the experiment runs and say it would not be an experiment with a time scale of this fair stuff, but a time scale of 10 years, and then this experiment disappears, then the code base is not maintained, and if there are some other people relying on that, then you have a problem. The same thing happens with root. So this started also as a project for one of the experiments at CERN, and then CERN realized that they need to put some manpower and some money on it. So without that, I think root would not have survived till now. So I think you need somehow supporting your ideas and paying your bill in the end.
Maybe if you allow me a follow-up question. We know that root has many 10, 30,000 users. Not everybody is working on the core, though you said like the boundary between developers and users is fluent. I mean, like it's also like for GNU Radio. I mean, like it's not a strict, we did the track differences, but the continuum is fluent. How many people do you think are actually involved in the core maintenance of root? This may be a follow-up question for you or for you. How are they actually doing this maintenance work to keep it alive for long term? And how many are there actually? How many, or other way around, how many people do the core maintenance now? But how many do you think should be? Do you have enough, too many, not enough?
Yeah, I think that Florian is, from the experience of root and fair root.
So from root, I can only guess. I would say the core team is in the order of 10 people at CERN and some other people at some other labs worldwide. But that's only a guess. And the problem with root is they don't do only the maintenance but also some development, but I think the development really is done now outside of the core group, and probably the core group is doing mostly keeping this thing stable. With FairRoot, I would say we have here 4 to 5 people at GSI, and then the experiments are sharing. So, but the maintenance is really mostly done here at GSI.
Yeah.
And I would say currently the development is also a little bit frozen. So there are no new requirements currently from the experiments. So everybody is more or less happy. It's more cleaning up meanwhile and shaping the project in such a way that it's maintainable. So I think the same thing you do now or try to do with GNU Radio 4 to keep things fit for the future.
Yeah, the same is also in PandaRoot, which is a thing on top of FairRoot, right? It's using FairRoot. Also there, at least I see the code developments of what's going on. I mean, you basically have at the moment maybe 3 real developers, but they're now mostly maintaining it and making bug fixes, and this is it, right? And then you of course have a user community, they're doing their own macros and whatever more, but that's not really part then of the intrinsic code, if you want.
I should maybe also express a thank you, Lord, to Florian, but also Matthias and Dennis and others, and also Mohammed, who mentioned that they were open for collaboration to share maybe at least the technology stack on the low-level end. And I think we should see that we have more synergies between these projects. So big thank you, also shout out to those.
So I'm curious, how do you, like, if you think of data processing, what's your mental model to like go from a DAC to your event acquisition and whatnot? I mean, you had pictures with pipes and whatnot, but how does that look in particular? Because I mean, I have a communications background, so I have my idea of how should a graph-based signal processing pipeline look like, but that might differ from what you would expect.
Well, it also differs from experiment to experiment. If you look at Alice, they of course focus very much on high throughput, so their model is very much on high throughput kind of things. If you look at Panda, it's a different kind of concept. There you do not have, let's say, many tracks or so which you have to analyze, so not really high throughput, but there you really have to think more about how to extract high topology from your event. So there are the models. So that really depends on what kind of experiment what you're dealing with. CBM, Alice, it's all more or less data models, high throughput data models, whatever that means. You have to ask the expert on that, right? But yeah, but this changes from other one to the other collaboration. So that's not really, let's say, as far as I know, unified. For instance, using this actor model, right, this fair MQ, this is something already on the transport level. This is not really, but on top of that, yeah, that is really experiment specific, I would think.
Okay, so I have questions around the transition from the offline to the online in situ processing. And if the whole collection system had to be built, like the early days, they were like 3.4 terabytes a second, right? So you had all the data, and then you're going to go grind on it for a long time. And then you build this thing where the data is reduced in flight, and you get this much lower data rate out. How do you know it's right?
Okay, well,
and then how much beam time does it take? How long does an experiment take? And I mean, I'm sure there's some model or something in here somewhere.
Yeah.
But how do you know you're right and you haven't just lost it?
Yeah. No, of course, that's a good question. I mean, well, first of all, what you do if you do an event selection, you also have something like a minimum bias, where you also have a certain set of fraction, but then just reduced by a random scaling of your total data flow, right? So you can always see whether your algorithms, what you're trying to do, by analyzing both the non-selective flow, which is reduced, which has been scaled down with respect to what you have selected, right? So in that way, you can always test that you're doing the right thing. So it's not like we only taking events where we look at a specific topology. No, also a fraction of the data we always take from anything, but we just scale it down, right? Now, in typical experiment, what you do for FAIR, if Panda or CBN will be 2 months or so. This is typically the block of time where you can think 2 months CBM, and then if Panda once comes, also typically 2 months, and then New Star also 1 month, and it's about in total I think 180 days of beam time, and the rest is machine things, right? I mean, so that's the typical scale one has to think of.
Thank you.
Coffee?
So I have a little bit different question. So it's known from other experiments, like from NASA sending satellites, that some old tapes with data were found which were still not processed. So I wonder what happens if you generate more data than be processed. So basically 10 years afterwards, people find a lot of data and don't know, is it still helpful?
Yeah. This is so data preservation is a key element which also has become more and more important, right? So this is, for instance, so there are, let's say, consortia, also the European Open Science Cloud. They try to now also enforce collaborations to take, data preservations to have it findable, accessible, interoperable, and reusable. I think the R you're talking about very much, being guaranteed. So nowadays, I think, to be very honest, right? If somebody would give me the tape of my data from my PhD, I would not even be able to analyze it anymore, right? There's of course always a lifetime. There's always a lifetime, but at least one is trying to extend this lifetime by installing these FAIR principles, by having this European Open Science Cloud, and so on and so forth. And also collaborations are now more enforced in order to get funding for whatever, for the activities to ensure that this is being done. But as it is always a lifetime. I'm sure in the 50s from years and the experiments that are now being taken, I don't believe anyone will be able to look at this. Probably better to just run an experiment, it's faster. Right. But yes, but this is an issue. Data preservation is a main topic in data management these days. Yes. And also there, for instance, AI could help, if you think about it. But okay, this may be on the higher level, but to go to original data.
Okay, so this is all the time that we had for questions. If you have any more, obviously, just catch to Johan at the coffee break, and let's thank the speaker yet again. please take your seats. We cannot really be late and we cannot delay because we need to leave this room at 12 o'clock. Just a reminder for the photos and for the group photo before the lunch. So I wanted to say let's welcome Gerhard and Thomas to the stage, but they're already here. So I'm just going to move away and the stage is yours.
Perfect. Thank you, Ivan. Hello, everybody. Is this, it's working? I'll give you just a second to grab the last coffee.
Hello? Bueno? Yeah, awesome. Great.
Oh, we got the technical stuff sorted now. Perfect. All right, let's start. My name is Thomas Weible, co-founder and CTO at Flex Optics. We are mainly in the optical transmission, but we heard from Johan. More up? Here we go. All right. That the transmission part is also quite important when you have a massive load of data. And the topic we brought today is more a game changer, and we show later on what's happening now in optical transmission and where we think it's a game changer. It's about coherent modules and coherent transmission. We split that presentation in two parts. Gerhard is introducing himself. Later on, he's doing the theory, and I'm doing or showing the technical example how we did the implementation with the coherent pluggables together with DKICs. So, give you a short intro where we are coming at the moment or where we are at the moment when it comes to de facto standards in terms of transmission speeds and applications. It is about 100 gigabit currently, state of the art, what we do when you interconnect switches, routers, and also high performance computers. And there are some drawbacks, those acronyms, the CFP and CFP2, these are form factors used to do or to enable the pluggable transceivers. And when we look at the CFP, for example, it was a great design in terms of we were able to put a lot of components in that pluggable module, but it had a huge drawback. It took a lot of power, and it was, in terms of size, it was really big. And when we compare them, there was some evolution with the smaller form factors, the CFP2 and CFP4. And the latest one, or the one which is mainly used, is now the QSFP28, which is a nice, tiny form factor. Having, again, a drawback, it cannot take that much power and cannot consume that much power. And when we want to connect long distance links, like 40 kilometers, 50, 60 kilometers, we need some power. And so this whole 100 gigabit ecosystem was mainly designed for inner data center links and within metro spans. Now, for longer links, DWDM, dense wavelength division multiplexing, is used still. And to enable this, a DSP is used, doing all the modulation there when it comes to coherent technology, but with the effect that it was a big chip and a big size of chip placed on a line card, comparing now with the current solutions doing 400 gigabit. We have now latest technologies doing really tiny structures on chips to 7 nanometers or even down to 5 nanometers. I'm aware there are other techniques around to do 3 or even 2 nanometers, but we are still in the telecommunication world and not in the AI chip and CPU and GPU world. So this is a big advantage now, having 7 nanometer structures, getting a small tiny DSP with a certain amount of power it consumes and the size. And those DSPs are now placed on a module doing 400 gigabit and enabling coherent transmission. So that's the current state, and I hand over to Gerhard. Oops, sorry.
Thank you very much, Thomas. And yeah, welcome. Oh, the light is hitting on me. Let me switch a little bit and talk about some theory about transceivers and coherent transceivers. Yay! Coherent light. Do we not already have that in transceivers? No, not quite. A transceiver could be an LED that just shoots light. With coherent transceivers, the speciality is that we want to detect more properties. But more on that. Talking about light, what we usually try to push are our bits, like you can describe it by step functions, but when you measure it in reality, what you see in your oscilloscope is something more like that, because nature, how it works, you always have a transition, obviously, through your values, so there are never these perfect jumps we want to have. And the thing is, this is an easy way to, really very simple way to describe how transceivers work. And if you want to increase the bandwidth, what you usually do is increase the frequency. Increase the frequency and you get faster and better. Like with the CPU in the 19s, more gigahertz, more power. But, of course, you're also hitting limits. And let me show what it is, because if we increase the frequency, like increasing the steps, and we want to detect for the photodiode our signal, we have to change our threshold. Now you see here, we have -1 and 1, so that is your threshold you could put and say, okay, this describes my 1 and my O, whatever, and now I have to change it. I have to put it on 0. Okay, we are fine, we can do this, but we have a smaller margin of detection. And if we continue doing that, it becomes even smaller. Like, look here, we have a 0.75 of threshold, which represents for us a 0, and like 1, detecting that in an exact manner is quite difficult. And yeah, getting a little bit to, maybe you have heard of the eye diagram. What is the eye diagram? Usually when you have an oscilloscope and you have a frame that is moving with the signal and you are measuring the signal quality, what you end up seeing is sinus wave upwards and sinus wave downward at the same time. Just imagine you're folding it a little bit and you have like an O here, and this looks like an eye. And if the signal is not precise enough, you start to see odd odd points there and lines and so on. So that is one thing. The other thing is, I was talking about coherent light. I was talking about amplitude, right? 1 and O, and where's the threshold to measure through the photodiode. Now, the light has more properties, and it's a little bit unfortunate that we have, we have been trying to discover that current transceivers isn't a technology that isn't that new, but what is new is that we have that small pluggable form factors where you can, with the proper DSP, with the current technology we have, 7 nanometers, really manufacture something like that. So what are the properties we want to look here? Let me start with polarization. It's quite simple. Polarization, I don't think I need to explain you what this really means, but to give a small example, which we usually come up with, who has a screen protector on his notebook? Who has it? Do you use it? Like, you watch from an angle and you don't see a picture because you want to protect that others don't see it. So that's the idea, and we are reversing this a little bit, because if instead of a diode we use a laser that shoots coherent light, we can also rotate this laser. We can calibrate it a bit. So we just shoot the signal wave over a plane, but we have a second plane, because you have the z-axis, but you can also rotate it, and you have another sinus curve. So when you combine them, you can add them vectorically. What you get, or you could see it as a diagonal plane that is moving the whole time, and something you can configure yourself. But you can split it up into components, because we have 1 dimension for the axis and 2 dimensions left for the area of your transceiver, of your fiber cable. So basically we have 2 planes, and if you rotate the signal, this is now in combination with phase shift. I'll get into this in a couple of minutes. It looks a little bit like a sinus wave, but since we have phase shift, it doesn't look as such. But imagine we don't have phase shift, it would be more like a sinus wave. So this is a signal you, through a simulation we calculated, you would get when you are checking current transceivers. Now if I rotate it even more, you see it becomes a little bit volumetric, and what you're really seeing here is the signal of a coherent transceiver. It transports a lot of information, and polarization has advantage. Since I'm talking about two planes we can benefit from. Of course, you are doubling the bandwidth already. So by just using polarization, you already doubled your bandwidth. Yeah? But that is one thing. The next thing we are going to observe and improve, and that's something we also can do with the current transceiver, is phase shifting. Phase shifting, as you have seen it in Wi-Fi networks, can also be used when you transfer current light and measure it at the other side with a local oscillator and a mixer. So OO key is the most simple constellation. What I'm showing here is an imaginary component. It is also called Navier-Jarrell quadrature component. Then we have the in-phase component, which really is the real axis. And yeah, this is basically the center. So on off is another description of what I showed of a non-coherent transceiver. But now let's dig deeper and try different constellation. PAM4 is when you use different amplitudes. We are still not at the coherent part. But now we are making it more interesting. Now we have 16 combinations. And with 16 combinations for one frame, you're pushing way more data, way more bits. And that is the advantage you can achieve with coherent transceivers. Obviously, it requires a DSP, but that's the idea of it. No? Maybe getting a little bit back to a very simple kind of transceiver, maybe, or I mean, it is related to some optical interaction you have here. We are defining one detector as the real part and the second as an imaginary part. But the question here is, I like to ask, why do you think we are doing that? Why do we have a rotary disk, and why do we need the imaginary and real part? So we have this rotating disk that produces a signal of a given frequency. So sometimes it's covered, sometimes not, depending on the orientation of this disk. But the question I'm asking you, to your as an audience, why do you think we need two readers? What's the purpose of the second reader? I mean, it's imaginary, I get it? Yeah, the question already was answered, yeah. Any ideas what it could be? Okay. The thing is, if you have phase shifting and you look at the signal and imagine you're moving it, you can determine the direction. If you want to measure, for example, rotational speed, into what direction is rotating this disk, you cannot find out with just one reader. But if you get a second one and you check the pattern, which part is on one in real, and the imaginary part, when is it on one, and what kind of phase shifting we have, you can find this out. You can see in which direction this disk is spinning. So yeah, that's another example. And we are getting back to the 16 quamp signal. I prepared a play of cards for you. And what I'm going to ask you in this small game is, you can see your cards on the table. I want to know who is transferring 1, 1, 1, 1. 1, 1, 1, 1. Yeah, right? So if you want to transfer that series of bits, we have to look for the point. What amplitude do you have to set up your current transceiver, and what phase? Can you tell me that?
I'm the center of the diagram.
Ah, yeah, by the way, here's the center.
The middle.
So if you look on your table, which card is it? Any idea which amplitude and phase we have? Yep, that's it. So 45 degrees, where is it? Center is there? Right, yeah, got it. So that was for warm up a little bit. Now let's try with 0101. Where do we have it? A little bit tricky because I covered some numbers. It is here. So what angle do we have here? Yeah, right. Awesome. And last one. Last but not least, we like to say 0011. It's around here. Yeah. Thank you. So with that, I'm calculating this as packaged. The audience was very reliable, 0 error rate, because if we want to calculate the error rate, the photo detecting system I call it, doesn't mistake on that regard. The bit error rate goes high, right? And for that solution, yeah, we have a couple of solutions like forward error correction. That is something you can do. The audience doesn't need that. Perfect. Thank you very much. And getting to the next slide, signal quality is another way to measure it. That is the view of an electrical engineer, signal and so on. We like to use dB because, you know, it is based on decibel, logarithmic. Log A times B is the same as log A plus log B. And if you applying an amplification of signal, you can just add it. But the idea is really with signal to noise ratio, how much useful signal to have compared to the noise. That is here you don't want, because you always will have noise, right? Then ESNR and OSNR, yeah, there's a difference between electrical and optical, obviously. You have electrical connection to your transceiver. Optical is what goes out, the light, or current light. And to give you some examples how the 16-QAM constellation looks when we have a transceiver with some simulation I made, some statistical application based on the Gaussian curve, you know. If we have a good signal-to-noise ratio, which should be high, like the curve I showed you before, the constellation looks like this. So if you put here your mesh, you can still clearly, as a photo-detecting system, find out to which bits it belongs. But lower this SNR gets, well, it gets worse. Here you can still detect, but here you don't know. Maybe some of these spots was hit there, but it was meant to be transferring at this area. So 5 dB is not a good transception. You're getting closer to your noise, and that is what you want to avoid. Well, that's enough about theory. I hope I didn't bore you too much, but let's get to the practical part. Thank you very much.
Thank you very much, Gerhard.
Yeah.
So what we did is we took a pluggable module, looks like here in the middle, and talked to DKIX in Frankfurt. They operate one of the biggest exchange around the globe. And the GSI and FAIR network is also connected to the DKIX. So when you're surfing the internet, you will most probably be transmitting on those modules. So we plugged it in their routers and looked at the command line interface, basically how the operating system is recognizing those modules, and especially which new parameters we're gonna see. So it was pretty simple. We were basically running a show port command on the Nokia operating system. DKIX is running Nokia gear. And there are basically 3 sections on that interface. The first one is more about the physics of the module, or the technical capabilities. And we see here it's a 400 gigabit module doing DWDM fully tunable from the start frequency of 191.3 terahertz. Actually it's shown in megahertz, but it's a huge number with a lot of zeros, so typically we talk in terahertz, to the max frequency of 196.1 terahertz, or way simpler, channel 13 up to channel 61, which is way easier to talk about. It's currently tuned to channel 23, and the nice thing about those Korean modules as well is it's not only tunable, you can also select the grid in which we want to slice down our DWDM network, which is quite convenient, and we are not tied to a certain grid. Well-known grids are 100 gigahertz and 50 gigahertz. Yeah. The second section is about diagnostic values and diagnostic monitoring, and everyone who is operating these kind of components, those switches and routers, is really aware of doing a monitoring of those modules, and there are 5 well-known parameters. It's the voltage, it is the TX and RX power levels, and it's the bias power or current going through the laser. And one important one is now also the temperature. And why do I highlight the temperature? Because typically in the past, the temperature was not so important to monitor. We were always in range. Now, when we look at the figures, in optical transmission, the math is quite simple. So we feed in a lot of power, and typically those tiny modules take 17, in some circumstances up to 20 watts, and we have not only one module in such a switch, we have 20, 30 on a small dense unit, and we convert it basically to heat. And the major electricity, the major watts are converted to heat, and only 0.001 watt is converted into a light level, which actually is 0 dBm, which is a really low level of light we get there. And therefore we have, because we have heat, we have to monitor and take care about the temperature quite well, because otherwise we will overheat the whole thing. And the third section we saw there are now the coherent parameters, and they are quite new to the optical transmission world when it comes to the pluggable modules, and I will go through them now step by step. So the first one, what we saw there is the RX channel, and typically when you talk about a tunable transceiver, you think about the laser, the TX channel, which you tune. Now with coherent modules, you have also the capability, when the physics are able to do it, that's a really important note, you can also change the receiver channel if you want. And if you want, and why would you do that? You can do this, for example, if you want to do a single strand transmission, so doing, instead of you running two fibers, one for transmit and one for receive, you can do it on a single fiber, having two different frequencies on one fiber, basically. But to do so, you need a separate local oscillator inside, and not all modules does support this. Then the next one is about dispersion. We have basically two types of dispersion on an optical fiber. There are a lot of dispersion types, but for this type of transmission, it's about the change or the change of the velocity while the light is traversing on our fiber. We have the chromatic dispersion, and this will change the longer our span is. The great thing is we can compensate it now with the effect of the DSP. We can do the math and do calculations on it. This link we were operating was a span of 15 kilometers on a regular single mode fiber, a G652. And this has, when you look at the characteristic of such a fiber, it has roughly 10 picoseconds per nanometer per kilometer of the chromatic dispersion. And when we do the measurement, we got 220 picoseconds per nanometer. So when you do the reverse mathematics, you can even calculate your link span. This would end up in 22 kilometers, which is not true. We were running at 15 kilometers. So we weren't quite sure where this offset is coming from, because we did a back-to-back link with only 2 meters of cable, and then we saw there 80 picoseconds. So there was somehow an offset, maybe of some not proper calibrations. We were not quite sure where it was coming from, because the actual fiber was 15 kilometers. Beside the chromatic dispersion, as Gerhard mentioned, we have now two polarization planes, the X and Y plane, and also the velocity of the light between those two planes can differ now. And this is the different group delay, or also polarization mode dispersion. And we do this also measure in picoseconds. This link had a delay of 2 picoseconds, and we are able to compensate up to 10 picoseconds with the module, but not more. Moving on, OSNR is now really important to monitor, and we have again two OSNR levels. We have one on the X plane and on the Y plane for the two polarization directions. This link was running at 34 dB, which is perfectly fine. We can go up to 24, 26, depending on which standard we are following. And then the bit error rate will go really, really up, and we are having flapping links or even a broken link. And there's another value which is quite helpful, is the RxQ margin. Here it's running at 2.4 dB. This is basically the margin, our forward error correction, which is also part of the digital signal processor, where the forward error correction is still capable to correct errors. So when we eat up this margin down to 0 dB, then the forward error correction is not able to work within specification and provide a proper bit error rate. And yeah, this is in correlation also with the prefect error rate, which is 10 to the power of -3, which is perfectly fine. And this margin, when you have a really back-to-back link, only with a couple of meters, is roughly 4.5 dB. The great thing now with those modules, and also with the fact that we have the possibility of the DSP doing the modulation, doing the forward error correction, we can even modify now the way we want to operate it. So it's not a pure 400 gig module. It is somehow we can support a couple of applications doing, for example, 2 times 200 gigabit or 4 times 100 gigabit, or even some odd numbers like 1 times 300 gigabit. It's just to the fact how we do the setup of the DSP and how we want to operate it. And the drawback is currently, or what we have seen is, there are no checks. So for example, this module is set up to a compatibility called OpenZR Plus, but actually it's not capable to do it, because when we look at the first section, it does only support 2 application modes. The first application mode 1 and 2, the first 2 top ones, and the configuration of the switch itself said, hey, I want to do another application mode, but actually it's not supported, so there are no checks in that operating system. And as I said, there are a couple of de facto standards or industry standards out there. There are 2 major ones. It's the OIF 400ZR, defining typical TX and RX power levels, but also now for the coherent modules, the dispersion, the critical dispersion values about chromatic dispersion and the PMD, and the OSNR tolerance. And the second one, that's the one which is currently the most interesting one, because it's slightly newer, but it gives more flexibility, especially when we look at the OpenZR Plus standard doing the 60 high power HA, having a huge launch power of 0 dBm. And why is this so important and critical? With that, we don't need external amplification to boost up to 50, 60 kilometers, which is quite handy and great. And also when you look at the chromatic dispersion, it's way more tolerant for longer distant links, and that's actually very, very handy. To sum this up, as I said at the beginning, the DSP inside of those modules is now kind of a game changer in optical transmission. And when we look at this graph, it's pretty much obvious. So the green dot here is typical pulse amplitude modulation, where we are currently, or what we can do. But just due to the fact with raw compute power, we are able to quadruple the amount of data on the same type of module. So coming from 400 gig, we can easily reach 1.6 terabit, for example, just of the fact using a different modulation scheme to dual polarization 16 QAM, for example. Another possibility is to increase the overall frequency, what also Gerhard showed at the beginning, but there are currently definitely limitations on the electrical substrates using for PCBs. We are already at 50 gigabaud, which is a really high frequency, and we can do in mass production 100 gigabaud, and that's also used now for 800 gig and 1.6 terabit. Brings me to the end, almost in time. Thank you very much for attention, and for sure we are around, and if there are questions or if you want to dig deeper into it, how to do the implementation, maybe on your equipment, we are more than interested on it. Thank you very much.
Thank you for the presentation. We have a time maybe for 2 questions at most.
Hi, thank you for presentation. I was interested to see that you are able to measure the dispersion by looking at the digitized signal coming out of your receiver. Do you see on a long link how it possibly changes over time, the dispersion? And by how much would that be?
Yes, the values we can see when they change over time. We basically have to put them in our management system, yes. Yeah.
Okay. So is that temperature dependent or aging?
That's a good question. To be honest, I don't know the figures now at the moment because those links are not, they are running maybe for a year or two. We haven't seen any degradation so far. Being on the long run, I can't answer that at the moment.
Okay, thanks.
What is the sensitivity value for different modulation techniques? I mean, I saw its minimum RX power is minus 12 dBm, but what kind of packet error or bit error does that correspond to? It's 10 to minus 3, 10 to minus 6?
No, the aim is typically defined from upper layers, from Ethernet, times to the power of minus 12. That's our aim, to get there after the forward error correction.
Yes, but with what error percentage, with what error rate?
So you mean how powerful the forward error correction is, how many errors they can correct?
No. If I input a signal at minus 12 dBm, how much of the packets can I get without any problems, without dropping it? After or before, that depends on the definition. You know, as we get closer and closer to, as we reduce the SNR level, the signal starts getting distorted. So we automatically lose some packets, some sort of chunk of data. So I'm wondering if the receiver, how the receiver is capable of with respect to input power. So if for example, if I put minus 10 dBm, will I be able to recover 100% of my packets or like 98% of my packets?
Okay, now I got it. So, okay. These specifications I was showing the minus 12 dBm. That's within the specification doing typically to minus 12. You can go lower, but then your bit error rate will go up.
Okay.
And the need is for the upper layers, like the Ethernet layer typically, we need the 10 to the power of minus 12. Okay. Otherwise we have, then TCP also will jump in as well and wants to do the retransmission and so on.
Okay. And also I would like to ask, what is the minimum EVM value that you have aimed in your transmitter design? So rather than SNR, EVM is a better tool to measure the signal quality?
Sorry, can't answer that moment.
Okay, thank you.
Okay, that was all the time that we have. Thank you, Gerhard and Thomas. And it was fun, even if I spent most of the time looking at the watch. And now we have a lightning talk by Andreas. So, while Andreas is setting up, just a reminder, we have a photo session before lunch. And we'll also have an announcement for the lab tours before you go. Or do you want to do it now? Okay. And now, yeah, give a warm welcome to Andreas.
Hello, guys. So last year, when we were in Paris, I got inspired to enable the GNU community a little more to make nice timing applications with cheap equipment. So I set myself out to build the cheapest GPSDO just yet. Bear in mind, it's a work in progress, but there is some progress. But I don't quite like the normal DIY approach that you find on GitHub most of the time, which is a lot of discrete components, analog PLLs, discriminators, a lot to solder, long warm-up times, Arduinos with mini USB, endless debugging and analog debugging of that. I'm a software engineer, I don't like that. Those things are often afraid of open windows, and I said in my mind, maybe we can fix that. So goals are no clock BS drift. By that I mean, if I just sync my time once and I record over hours, it still has to be the same amount of symbols. The GPS DLO must not have a residual drift that is uncompensated for, that the recording is shorter or longer. That is very good for TDOA applications and simplifies the process a lot. It should have a quick warm-up and correct the sawtooth effect, which is the alignment error between the clock and the GPS receiver and the PPS signal. You can see how this normally looks like, that you always have a plus minus 10, 50 nanosecond error on top of your PPS signal, by which you do your time synchronization. And yeah, I want to maintain less than 0.5 parts per billion, even if the window is open. This looks really neat. That's LIA M8F, where they played a really nice trick, where the GPS receiver, that knows a lot about its frequency offset, is disciplining its own oscillator. That enables it to, within its DSP, already estimate the frequency offset and tune itself to compensate for that. For example, with the nav clock message that has the so-called clock bias, that is a regularly updated value of the drift between the receiver's clock and the GPS clock in nanoseconds per second. Just null that value if you control it and you have synchronized your clock. It's actually quite easy, and it's all software for what I'm concerned. So, and the sad thing about this module, it's the wrong weight. It's for LTE base stations, so 30.72, and it's also no longer recommended for new designs, but I really wanted something like that. And I should have read the publication of Mark Seboklis, who did a very nice analysis to such an approach. He DIY'd this with more of a textbook approach of an analog devices, a PLL to generate a 26 megahertz clock out of his 10 megahertz of an oscillator, disciplining the U-blocks and doing all those funny games. This already looks like a much cleaner setup, more what I'm looking for. So let's make this even simpler. I replaced the microcontroller and the PLL and the little oscillator here to that completely by the Raspberry Pi 2040 by utilizing the CPU PLL, which when you set it to 104 megahertz, those are the settings of the PLL, you can actually generate quite a nice 26 megahertz signal, much better than I would have anticipated for a CPU clock. And that feeds directly into a U-blocks receiver where I just soldered the clock out. And yeah, there's like $10 worth of components there. And by which with those components, I build a little test bed with the resampler as well as the OCXO, a little stabilized PVM DAC, and there's really not much to it. And this is a finished setup that I tested on the weekend the first time successfully, and it works. The blue chart, you can see the clock bias, the offset in nanoseconds per second, and when I try to null it, I have a really nice 10 megahertz clock. The nice thing is, once I approach this point, I also get this quantization error, the sawtooth effect we saw earlier. This is also reported by the U-blocks chip, and it's reported in picoseconds per second, so a factor 1,000 better than the clock bias. And when you're that synchronized, it is the clock bias. So my control loop is then switching to trying to null the quantization error. And as you can see, it actually works. Before it has a lock, it's still oscillating between plus minus 10 nanoseconds. And the moment I get a proper lock, I'm much closer to 1 nanosecond. And I found a bug, so that was with a broken control loop. I'm anticipating to perform even better. But this is already, 20x improvement over the data sheet. And it's actually physically correcting the quantization error instead of you having to do this later in software, which is quite nice. The files will be on GitHub, probably at the weekend. I'm from D-Drone, I'm a software engineer there. We detect drones, we do all kinds of fun stuff like this all day, and we're hiring, so that's a little thing for marketing here. I have leftover PCBs. If you want one, build this yourself. It's a really fun experiment to do. Thank you very much.
Thank you, Andreas.
Are there any questions? Maybe one?
Okay, thank you for not having questions because we don't have the time. But obviously, catch him afterwards and I don't know. At least that was what I was told. No? No? For the love of God. And this is in German.
I don't like Windows.
Okay, the PDF seems to block the picture.
Good enough. We can work with that.
Okay. How can I put this on? Hello? Hello?
Okay.
Yeah, okay.
And you're David, right?
Hmm?
You're David.
Yes.
Or David or?
David.
David.
Okay. Thank you.
Okay, here you go, David.
Okay, yeah, hello and welcome to this lightning talk about how you can do radio direction finding using GNU Radio and an Adcock Butler matrix. So first of all, a few theoretical fundamentals. So what is an Adcock antenna? An Adcock antenna was invented and also patented from Lieutenant Frank Adcock in the year 1919, so it's very long time ago, but it's still used in radio direction finding. And yeah, it consists of two monopole or dipole antennas, and they are phase reversal combined to get this H-shaped radiation pattern what you can see here. And yeah, an Adcock antenna array, this is what we used here now. It consists of two orthogonal Adcock antennas. So you can see here a north antenna, a south antenna, east and west. And so the north-south pair is phase reversal combined and the east-west pair. So this phase reversal combining is done with a 180-degree hybrid coupler. So these are these two outputs, and this 180-degree coupler gives you also the sum if it's used as combiner. Yeah, so in principle this works as a circular interferometer. Yeah, so the signal which is impinging on the north antenna, so at this output, this is our reference output. So yeah, the signal which impinges on all antennas gets no phase shift from the Butler matrix. And at this output, so the signal which impinges on the north antenna gets also no phase shift, but on the east antenna you are obtaining a 90-degree phase shift, a 180-degree phase shift at the south antenna, and at the west antenna a 270-degree phase shift. And yeah, between, so if the angle of arrival is like 40 degree, because of this coupling, it will be here interpolated. Yeah, so here you can see this 180-degree hybrid coupler in the UHV band. It can be built with lumped elements. So it's very small, and you can see it here. And here you can see this mini circuits blocks in the anechoic chamber. Yeah, so these two ports has to be progressed by using GNU radio. So we use the USRP B210 with 2 channels. And afterwards we're using a frequency X-lating filter to decimate the signal further and yeah, to get rid of the DC offset. And then we do this to compare the phase channel with the reference. This is done by this division block. Then we are doing a moving average to get a more stable result. And because we are only interested in the phase of this, we use a complex to mag phase block. And the magnitude is neglected. And yeah, we're doing a radians to degree conversion here and feed it to a compass. So these blocks are all available. Yeah, so no other blocks. And here you can see the measurements out of the anechoic chamber. So this is a Watson-Watt principle. So you normally use 3 channels, but yeah, I used 2 north-south and east-west outputs. So here you can see this H-shaped radiation pattern, which I told before, and the estimated phase. But you can see you have an ambiguity of 180 degree. And here you can see the results of this 180 degree hybrids, which I built. And you can see the phase can be obtained, but there's a little bit of sinusoidal error. And yeah, this is because of one of this 180 degree phase shift was not very balanced, and you got an amplitude error of like 30 degrees. But yeah, you can still see that you can estimate the phase. And yeah, I'm also from Deteron. I write my master thesis at the moment. And if you are also interested in such topics and looking for a new adventure, take a look. And yeah, we are also want to do a live demo now about it. Yeah. Okay.
Okay, next up is Mikhail.
Ears, luckily, and I guess there's a presenter somewhere. There. Okay, so let's see if I can do the full screen trick. Is there a trick? Oh? Okay, close everything. Open this. Aha. Control what? Control L. Okay, whatever. So hello. So this is whipped together in a rush. Just yesterday I was informed that there are some lightning talk slots left, and it's totally okay if it doesn't directly have to do anything with GNU Radio, as long as it's interesting. And maybe I can, most of all, like amuse you with some circuits. So I tell you a tiny story. So I work at the experiment electronics department. We do not so much work with continuous waves and phases and stuff, more like amplifying pulses from detectors to bring them to a level and maybe shape them a bit, to digitize them in the end and finally write them to disk at some point, yeah. Okay, so sometimes while student interns spontaneously appear in our department, something like my boss says like, oh, there's some student interns coming and there's a very smart one and I actually wanted to like deal with him myself, but now I have to go to this conference, like here's a student intern for 2 weeks. Don't do that. Yeah, so meanwhile, there's a hook loose. Oh yeah. We have some go-to projects in our department, and depending on the skill level and or motivation, we build something like a traffic light state machine with an Arduino, or a self-exciting magnetic pendulum, or we also build sometimes a photodiode, like from a cheap photodiode with some amplifying stages. You can, if you shield it from light, you can actually detect beta radiation. And yeah, that's what I built with this 11th grader. And yeah, it was actually Mr. Smarty Pants, and he was quite bright and was very hardworking and was finished with his radiation detector already like at the end of the first week. And it's not just building the radiation detector, he also learned KeyCut, and we actually built the electronics on a small laser cut PCB. And so he was eager to do more, and he found the other projects boring. So yeah, let's whip something together to keep him occupied and possibly build another board, yeah, with what he knows about KeyCut. And yeah, so I made the following offer, like we could transmit sound over a laser pointer. And he Googled a bit, and then after 3 minutes he found a YouTube video. Boring, yeah, okay. You just have your audio source, you somehow feed the signal into a laser pointer, then pick it up with a solar cell connected to a PC speaker. What's the big deal? Like, where's the electronics? Where's the fun in that? Boring. Okay, so I made the following offer. Yeah, but how about we do it in stereo? And yeah, first week was over. I went home. I grabbed a breadboard and components that I had laying around, turned on my oscilloscope, and tried to whip something together, hoping that I would finish in time to give him instructions to build this. And yeah, first, I think I do the demo now first, so it's more impressive if you don't know yet how it works. So, I have some receiver here. At the moment, it's receiving bullshit. So we have a tiny laser card board here. We have some DIP ICs on it, some op amps, and some logic chips. And the photodiode sensor is here. So this CD-ROM is actually like a practice target disk, so I can aim better, but it's like 5 by 5 millimeters. And I got a sender here, and I still need a signal source, which I forgot here. But it's all prepared in principle. Oop. So, playing back some audio, turning on the laser. Don't worry, I won't aim at you. Okay. And now I'm hitting the target disk. Okay. Turn up the volume at the sender. And it's Led Zeppelin, because let's zap that receiver, yeah? Haha. So, huh? Frank Zappa, okay, it's also good, yeah. And, yeah, now walk. And that's the best part, yeah? You can actually use this as an instrument. It actually sounds like a laser gun by coincidence. Okay, so, and I said it's stereo, yeah? So I have prepared another audio file. Okay, so it could be a mono file, like just saying left and right, but how about I disconnect one of the speakers? I don't know which it is. There's a tiny bit of bleeding between the channels, but okay, now the thing stopped, but yeah, I guess you heard it. We have stereo. Thanks, thanks. So, now I can actually explain what is happening there. So, I quickly photographed my concept drawings. I could have showed you the keycut schematics, but they are too convoluted with all the decoupling things and wiring the packages right. But a general concept is, first of all, any guesses how it's done? So also I can tell you, once the laser beam is in the vicinity of the sensor, it works and it doesn't change the volume with the intensity at the sensor. Just if you surpass a minimum amount of signal, it just works and keeps the volume stable. Close to it, but actually I didn't know which channel I was going to unplug because I didn't remember yesterday when I tested it. It actually keeps the channels, like the assignment of the channel stays constant, even if I yeah, cut the beam. Any other guesses? Okay, I already showed like a bit of the schematic. So it's actually pretty straightforward. I do a phase modulation. So first of all, like I generate a square wave and also a triangle wave, and they are synchronous. They come from the same oscillator. One is just the integral of the other. Yeah, that's the common op-amp basic circuit. And here is my audio. It just gets buffered and a bit amplified. And then I have a discriminator, a comparator, yeah. And yeah, the triangle goes up and down and up and down. And I have an analog multiplexer that for the rising edge of the triangle selects the left channel, and for the falling edge of the triangle selects the right channel, yeah. And so you have the left edge of the resulting square wave wiggle with the left audio, and the right edge wiggle with the right audio. Yeah. Then you have a tiny switching transistor, and you give this to the laser diode, and that's the entire sender. Yeah. So, how do you receive this? First, there's the receiver. It's also very, very simple. You have this tiny cheap photodiode, and I just used 3 gates of a hex inverter, an old CMOS hex inverter, wired as a very high gain amplifier. Yeah? And it's AC coupled, and with this feedback, it's self-biasing. So no matter how big the received signal is, it's always through the AC coupling located around the switching threshold, and once you surpass a minimum amount of visual signal, like you get a logic signal out again. And this feeds into the demodulator, and it's basically two old school CMOS chips. It's the classic PLL dip chip and two D flip-flops that are wired as toggle flip-flops. Yeah, how does it work? We have basically this PLL to lock onto the average of the leading edge. Yeah? And we have a very big loop filter. So basically the audio gets filtered away, and we get a waveform that is on average in sync with the received signal. Yeah? And yeah, then there's some gymnastics with doubling the frequency of the VCO and dividing it down again. So I don't want to get into detail, but it's pretty straightforward. So I can get a signal that is 90 degrees out of phase with my received signal. And this is basically something I can use as a mask together with an AND gate to, I mask this recovered, stabilized clock signal with the received signal, so I can cut out the wobbling of the right edge only, low pass filter it, and then I have my DC or audio. Yeah, and I can also do this with the inverse of this recovered signal, and then I cut out the left wobbles. Yeah? And yeah, then you can do some filtering, either second order cell and key, or it would probably just work with an RC thing, and then you get your audio. And yeah, that's it. So one weekend of tinkering produced a project that the student could build, could make PCBs, and it kept him occupied for another week until the end of his internship. And it really worked. He got it finished on Friday afternoon at 3 o'clock, and it just worked. And then everything was over, and he was happy, and he was allowed to take it home. And yeah, I showed you now a replica that I built myself. Yeah. Okay, that's it. Thank you. I hope that.
Thank you to everybody for great lightning talks. As you can see, lightning talks are really fun. So please submit yours even today and make the following days even more fun. Public service announcement, there is a photo session outside, but before that, here you go.
Yeah, we have now the lunch break. We are a little earlier, so I propose we meet at 13:15 outside here in front between the two buildings for the tours. So and then you look out for me and for Sharp. Where's Sharp?
We also have a live demo for the direction finder.
No, sure.
Sorry, one last minute announcement. We have this photo outside. We have a public event afterwards, so where there will be lots of externals. So if you have some hardware or your bags, I would suggest to take it with you, because this will be occupied just for this afternoon by another group. And then we would meet after lunch. First photo, lunch, and then after lunch in front for the GSI tour. And don't forget, this evening we have another social evening, but this is going to be at Kalkofen. You have in your tags the directions how to get there. Please let us know if you need some assistance or can't walk that distance. Thanks. Bon appetit.
Okay, yeah, so you can see the compass. It's also a GNU radio block, and now nothing is transmitted. You can see only noise, and the compass is flittering around. And now Andreas is transmitting a signal at 868 megahertz. And yeah, the compass is locked to the signal you can see. And if you rotate it a little bit, you can also see, yeah, the compass will also rotate. So yeah, you estimate the angle of the incoming signal. Thank you.